All right, in the world of data science and AI, there's this huge question, a really fundamental one that's surprisingly tough. How do we actually know what causes what? So today, we're going to dig into an idea that suggests the answer might be way simpler than we've been told. Okay, so for a long time, the main idea, and this is coming from the legendary Judea Pearl, has been that regular old statistics, the stuff that finds correlations, just doesn't cut it. He basically says that to really get at cause and effect, you need a totally separate set of tools, like a whole new language just for causality.
But, and this is where it gets interesting, not everyone is on board with that. You've got Andrew Gelman, another giant in statistics, who looks at all of these special causal models and, well, he thinks they just make things way too complicated. His take is that the tools we already have in our statistical toolbox are more than enough to get the job done as long as we're smart about how we use them.
So there you have it, right? Two of the smartest people in the field, and they have completely different ideas about this. It leaves the rest of us wondering, well, who's right? Is there a better, maybe simpler way to think about causality that can kind of bring these two worlds together? All right, to really wrap our heads around this, let's jump into a super simple real-world example. It's one that shows you exactly why this whole thing can be so tricky. We're going to talk about aspirin and headaches. So just imagine we go out and collect some data. We're looking at three things. First, how bad someone's headache is when it starts. Second, the dose of aspirin they choose to take. And third, how long that headache sticks around. Pretty simple, right?
But then we look at the data, and something is really weird here. It looks like, on average, the people who take a high dose of aspirin actually have their headaches for longer than the people who just take a low dose. That can't be right.
So what's going on? I mean, does this mean aspirin actually makes headaches worse? Have we been getting it wrong this whole time?
No, of course not. The data is lying to us. And the reason is something called a confounding variable. It's basically a hidden factor that's lurking in the background, influencing both things we're looking at and totally messing up the results. Okay, so here's exactly what's happening. That hidden confounder, it's the initial severity of the headache. Think about it. If you have a monster of a headache, you're going to reach for a higher dose of aspirin, right? But that monster headache was also probably going to last a long time no matter what. The data just lumps those two things together, and suddenly it looks like the aspirin is the problem.
So how in the world do we fix this? This is exactly the kind of puzzle that leads people to say, see, we need special causal tools. But what if we don't? A really fascinating new paper argues there's a much more straightforward way to cut through this confusion, just using the tools of probability that a lot of us are already familiar with. And the whole idea boils down to this one, really powerful mantra. The secret isn't just to model the data you see. No, the trick is to build a model that describes everything, all the possibilities, including the what-if scenarios you're curious about. They call this the twin model approach, and it's actually pretty clever. Here's how it works. First, you build a model of the observed world. That's just what really happened in your data. Then you build a second parallel model of an intervened world. This is your what-if world, where you get to play God and decide who gets a low dose and who gets a high dose. The magic happens when you link these two worlds together with some shared assumptions. Like assuming human bodies work the same way in both worlds. And boom, you have one big, powerful model that contains both reality and the hypothetical. And this is where it gets really cool. When you use that unified model to simulate the intervention, to see what happens when you force everyone to take a high dose versus a low dose, the results completely flip on their head. That confusing effect just disappears, and the true causal link shines through. Taking more aspirin does make headaches go away faster. We've totally untangled the mess. Now, this whole approach isn't just about what might happen in the future. You can also use it to look back in time and ask those tricky what-if questions about the past. We call these counterfactuals, and they are notoriously hard to figure out. So let's say your friend had a really nasty headache that just went on for hours, even after she took some aspirin. We can actually use this same probabilistic model to ask a super specific question. What if she had taken a different dose? What would have happened then?
The process is pretty much the same. You model what happened, and you model the what-if scenario. But the link between the two worlds is a little different here. Instead of a general rule, you anchor both models on the specifics of that one person. We plug in what we know about her situation, even the unobserved stuff, like the exact severity of her particular headache. Once you lock in that hidden detail, the model can tell you what probably would have happened.
Okay, so this is the big payoff. If regular old probability can do all this cool stuff, what does that mean for all those special causal tools we talked about at the beginning? Are they really a whole separate language, or are they just a different dialect of the same thing?
Well, from this point of view, something like Judea Pearl's famous do operator isn't some magic wand. It's really just what coders call syntactic sugar. It's a nice, clean shorthand for the exact process we just walked through. Building a twin model and simulating what happens when you intervene. And it's pretty much the same story for another big one called structural causal models, or SCMs. They might look all fancy and different on the surface, but this paper makes the case that deep down, they're just another way of writing down your probabilistic assumptions. They're just a very specific, sometimes even a more rigid, way of saying, here's how I think the world works. So who cares, right? Why does any of this matter? Well, it's actually a huge deal. This isn't just some dusty academic squabble. By reframing causality as a problem of probability, we're actually making it easier to understand, more flexible, and ultimately way more powerful for everybody. I mean, think about it. This way of thinking brings a whole army of people who are already experts in probability into the fold. It gives all of us more freedom to tackle weird new problems that don't neatly fit into the existing causal frameworks. Plus, it makes it way easier to do practical stuff, like mixing and matching data from different kinds of studies, all inside one single consistent model. So we land on the big takeaway here, a kind of updated version of that mantra from before. If you want to answer any kind of causal question, doesn't matter if it's about the future or a what if about the past, your first step is always the same. Build one single joint probability model that covers both what really happened and all the different worlds you're curious about.
And that's the really exciting part. This perspective doesn't just make old problems simpler. It actually opens the door to totally new possibilities. By thinking about causality in this universal language of probability, we're not just settling an old argument. We're giving ourselves the tools to start asking, and maybe even answering, questions that we haven't even thought of yet.